Yes. Hello students, welcome to BYJU'S Exam Preparation, the most comprehensive preparation app for all exams. Students, all of you, good afternoon. Welcome to the session. Welcome to BYJU'S Exam Preparation. Yes students, today a marathon session on power electronics. In this session I am going to discuss most important formulae for quick revision. Who are preparing for BARC 2021? Whatever the formulas that I will give with respect to power electronics, that is more useful, students. Yes students, all of you, good afternoon. Welcome to the session. Kanchi Maithili, good afternoon. Welcome to the session. Yes students, welcome to BYJU'S exam preparation. Yes students, before starting the most important formulae with respect to power electronics, first let me introduce myself. Yes students, my name is Surendra Babu. Yes, all of you, good afternoon students. For 10 years, I am educating the students for GATE, ESC and PSUs. I mentored more than 15,000 plus students. These are the subjects I am teaching for various competitive point of view: network theory, power electronics, electrical missions, power systems, control systems, electrical and electronic measurements, transducers and mechanical instrumentation. Yes students, all of you, very good afternoon. Welcome to the session. Yes friends, this is one announcement. The September special sale, flat 25% off on online classroom program for GATE, PSU and ESC exams. Use the code of extra 25. Get the 25% off on online classroom program, students, for GATE, ESC and PSUs. Yes friends, all of you, good afternoon. Welcome to the session, students. All of you, good afternoon. Welcome to the session. Yes students. Pramod Kumar, good afternoon. Welcome to the session. This is my Telegram channel, students. Who are not joined still now, you please join the channel for more updates about my lectures. And if you have any doubts clarification, you please share your doubts in the channel, students. Yes friends, here I am going to giving important formulae with respect to power electronics. Who are preparing for GATE, ESC and PSUs, it is more useful. And mainly this is particularly given, I am giving for BARC. For BARC 2021, it is more useful, students. Yeah, with respect to power electronics, by considering all the topics, whatever the topics are there for BARC exam, that I am going to giving important formula, students. The first one I am starting with respect to what are the important formula you remember with respect to power semiconductor devices. Yes students, the first chapter is power semiconductor devices. Come on students, all of you, welcome to the session. Power semiconductor devices. What the points you remember with respect to power semiconductor devices, students? Yeah, this is the chapter 1 with respect to power electronics. Yes students, with respect to power semiconductor devices, mainly you concentrate on the fundamentals and you concentrate on the power diode and also you concentrate on the thyristor. These three topics are very important: fundamentals, power diode and SCR, that is the thyristor concept. These three is very important, students. With respect to fundamentals, mainly you concentrate on how to calculate the switching losses, how to calculate the conduction losses. That two topics are very important. Here for example, students, let assume that if the current and voltages are changing like this, if it is given like this is very important observation. If the current and voltages are changing like this, it may be during on time or during off time, students. Yes, let assume that the current is the voltage is falling, current is rising. Voltage is falling, current is rising, students. For this type of characteristics, let the voltage is V, the current is I. This is voltage is falling, current is rising. The instantaneous voltage and instantaneous current. This is T. Students, current is rising, voltage is falling. That is the current through the switch is rising, voltage across the switch is falling. That is the meaning. Current through the switch is rising, voltage across the switch is falling. This time is called turn on time. This time is called turn on time, students. Yeah, if the current is rising, current through the switch is rising, voltage across the switch is, if the current through the switch is rising, voltage across the switch is falling, then it is called turn on time, students. This is called turn on time. For example, if the characteristics are given like this, if the characteristics are given like this, yes students, come on, concentrate. If the current through the switch is falling, voltage across the switch is rising. Current through the switch is falling, voltage across the switch is rising, students. Let this is the V and this is the I. This time is called turn off time. This time is called turn off time, students. Yes. Yes, Amit, good afternoon. Yes, Veera Reddy, good afternoon. Kanchi Uma, good afternoon. All of you, very good afternoon, students. Welcome to the session. Yeah, this here I am telling that voltage across the switch is rising, not the supply voltage, students. It is not the supply voltage. I am talking about the voltage across the switch is rising. Voltage across the switch. This is the switch current and this is the switch voltage. This is the switch current or device current. This is the switch current. This is the voltage across the switch. This is the switch voltage. Switch voltage or device voltage. Because every device is used as a switch. Every device is used as a switch. If the voltage is rising, current is falling, then it is nothing but a turn off time. Then it is nothing but a turn off time, students. Now I am asking one question, students. Yeah, the first very important formula is, what is the, here I am explaining about the switching losses. Calculation of switching losses. Yes, students. Average, the first one is average on state switching energy loss. Switching energy loss. Or directly I am explaining the switching energy loss. Switching energy loss. Energy loss, students. The switching energy loss. That is, this is the average on state switching energy loss. Then direct formula 1 by 6 VI into T on. On state switching energy loss. If it is asked, what the off state switching energy loss, students? Off state. During off state, what the switching energy loss? Then E into T off equal to E T off. That is during off state. This is equal to 1 by 6 VI into T off. Very important formulas. Then what the total energy loss? The total energy loss, students. The total energy loss equal to, the total energy loss is equal to, yes friends, E into T on plus E into T off. E into T on plus E into T off. This is the total energy loss. Yeah, this formula you remember. Similarly, if it is asked what the power loss? Yes friends, average on state power loss. Here I am giving what the average on state power loss, students. The third one is average. These all are switching losses. Average on state switching power loss. On state switching power loss. This I am giving switching power loss, students. The switching power loss equal to, that is a P average or P on 1 by 6 V into I into, this is during which state, students? During which state? V into I on state. T on into F. Extra we can get the frequency. See the difference between energy loss and power loss. Extra we can get the frequency term here. What is the off state? What is the off state, students? The off state power loss equal to 1 by 6 Vi into T of into F. T of into F. What the total power loss? The total power loss equal to on state power loss plus off state power loss. The total power loss equal to on state power loss plus off state power loss. Here I am explaining the concept of switching losses, students. This is one important. Sometimes the question may be expect like this. What the maximum power loss? What the peak power loss or maximum power loss, students? That is also important. Here I am giving one more formula. This is third, first, second, third and fourth one also, students. Very important. What the maximum power loss, students? The maximum switching power loss. The peak instantaneous power loss. The peak instantaneous power loss, students. The peak instantaneous power loss. This is also important. Instantaneous power loss. Can anybody answer this one? What the peak instantaneous power loss? The peak instantaneous power loss equal to 1 by 4 into Vi. 1 by 4 into Vi, students. The peak instantaneous power loss equal to, yes, Patel, is it voice is low? All of you feeling same problem? What about remaining students? Yes, friends. Is it voice is low? Yes, friends. Can anybody respond? Yes. Is it okay, sir? Any problem? Can anybody respond? Yes, students? Yes. Okay, thank you, Pramod. Yeah. Patel, please check your side. Please check your side. Yes. The peak instantaneous power loss equal to 1 by 4 into Vi, students. The peak instantaneous power loss. Yeah, this is the calculation of switching losses. But this formula is applicable only for this type of characteristics. For all the characteristics, it is not applicable, students. This is for linearly rising and linearly falling characteristics only. Yes, this is linearly rising and linearly falling characteristics only. These formulas are applicable. Yeah, that you remember, students. Next. One more important formula that I am going to giving students who are preparing for BARC exam. This is more useful, students. Then calculation of conduction losses. Calculation of conduction losses. Calculation of conduction losses. Yes, students. The calculation of conduction losses. That I given switching losses, but this is the conduction losses, students. We know that during the conduction of semiconductor device, it may be represented with only voltage drop or only resistance or both voltage. That is, it is represented with both voltage and resistance, students. That means, for example, during the conduction of any semiconductor device, it may be diode or SCR, BJT, MOSFET or IGBT, students. Any semiconductor device is represented. For example, it is represented with only, yes, it is represented with only voltage. That is, it is represented with only voltage drop or cut-in voltage. Let the current is I. Let the current is I, students. For example, it is represented with only voltage drop. How to calculate? The statement we can expect like this. A semiconductor device is conducting. The current through the semiconductor device as shown in figure. The voltage drop is given Vd. Then what is the average conduction losses? The average conduction losses equal to, if only voltage drop is given To find the average power loss, you can use the average current, students. If you use the only volt, if it is given only voltage drop, don't multiply with RMS current, you multiply with average current. One more important, students, if only resistance is given, if any semiconductor device is conducting, its on state resistance is R on and current through that resistance is I, then in this case, to calculate the average power loss, then you can use RMS current, students. Don't use average current. With respect to resistor, you can use the RMS current. I RMS square into R on. If any device is conducting, students, if it is represented with both resistance and voltage drop, come on, students. If it is represented with both resistance and voltage drop, the current through this one is I. But sometimes the current directly they don't give. They will give some waveform. From that waveform, you can calculate average and RMS values based on the given equivalent circuit. If both voltage drop and resistance is given, then how to calculate the average conduction loss of students? With respect to VD, multiply with average current. With respect to resistance, multiply with which one, students? With respect to resistance, multiply with RMS current. That's why VD into I average plus I RMS square into R on. This is the calculation of which losses, students? Conduction losses. This is also important concept with respect to fundamentals. With respect to fundamentals, this is also important. Yes, Amit Das. Today I will send the solution. Amit. For time being, I am not given that solution. Today I will send the solution. Amit. No problem. Yes, students. Yes. This is the calculation. This is one more important concept with respect to fundamentals of power electronics. Yes, friends. Then with respect to fundamentals of power electronics, another important concept is ideal characteristics of semiconductor devices. Ideal characteristics of semiconductor devices. Ideal characteristics of, yes, friends, ideal characteristics of semiconductor devices. Yeah, this is also important. With respect to fundamentals, we may expect the question based on the ideal characteristics of semiconductor devices, students. For example, if it is given that diode, yes, friends, if it is given that diode, what is the ideal characteristics of a diode? I am not explaining in detail how to draw all these. Just I am giving the summary formula, students. I am giving the summary points and summary formula. Come on, students, concentrate. Then if it is asked what are the ideal characteristics of a diode? Okay, this is the anode and this is the cathode. If you draw the ideal characteristics of a diode, yes, students, please concentrate. Yes. Let this is the I and this is minus I, this is V and this is minus V. Diode blocks the reverse voltage, allows the forward current. Okay, this is the ideal characteristics of a diode. Yes. The second one is, if it is asked what is the ideal characteristics of a, very important I am giving, students. Very important that I am giving. Yes. If it is asked what is the ideal characteristics of a SCR, that is the thyristor. If it is asked what is the ideal characteristics of a GTO, what is the ideal characteristics of GTO? This SCR and GTO is having the same ideal characteristics. This is anode, this is the cathode and this is the gate. Anode, cathode and gate. Okay, this is the symbol of SCR and this is the symbol of GTO, students. For these two devices, the characteristics are same. For these two devices, the characteristics are same, students. We may expect ideal characteristics. Draw the ideal characteristics. This is I and this is minus I and this is the V and this is minus V. All these two devices, yes, students, allows the forward current concentrate, it allows the forward current, students, and it blocks the both forward voltage and reverse voltage. It blocks the both forward voltage and reverse voltage. But the GTO reverse blocking voltage is very less. But the SCR reverse blocking voltage is more, students. But it blocks the both forward voltage and reverse voltage. This is the ideal characteristics of SCR and GTO. Ideal characteristics of SCR and GTO. Yes, students. That's why it is the example of which one, students? It is the example of which one? Unipolarity unidirectional device. Unipolarity. This also asking unipolarity and a unidirectional device. Unidirectional device. Yes, students. Unipolarity and unidirectional device. That means it allows the forward current, it blocks only one polarity of supply. Not unipolar I am talking. I am talking about unipolarity. Unipolarity in the sense it blocks only one polarity. What about this one, students? It is a bipolarity. Bipolarity in the sense it blocks the both the polarity. Bipolarity and unidirectional devices. Unidirectional device. Unidirectional device. This is also important model of question, students. One more important is we may expect the ideal characteristics for BJT. Yes, friends. We may expect the ideal characteristics for BJT. Yeah, this is the BJT. This is a collector, base, emitter. Yes, friends. I'm clearly drawing this one. Clearly drawing. Yes, friends. If it is asked for what is the ideal characteristics of BJT, that this is the collector and this is the base and this is the emitter. We may expect the question based on the what is the ideal characteristics of MOSFET. What is the ideal characteristics of MOSFET? This question also you can expect. Yes, friends, ideal characteristics of MOSFET. Yes, drain, source. Yes, this is gate. Yes, friends, this is the gate. This is the source. Yes, we may expect the what is the ideal characteristics of a MOSFET also. Ideal characteristics of MOSFET. We can expect the what is the ideal characteristics of. Yes, friends. What is the ideal characteristics of? Yes, which one, friends? What is the ideal characteristics of MOSFET? What is the ideal characteristics of BJT? And we can also expect what is the ideal characteristics of. This is the BJT. This is the MOSFET. Yes, friends. Okay, that gives the instantaneous power loss. Amit, instantaneous power loss is independent of the frequency, but average power loss is depends on the frequency. This is different. This is the instantaneous peak power loss. It's the instantaneous peak power loss independent of frequency. But average, that the term you can use, that is average power loss, Amit Das. Okay, that's why that depends on the frequency. Yes, Vishwajit Pant, I already taken the a marathon sessions on the power electronics. 2 sessions I taken. That's why I'm taking only formulas in this session. I already taken 2 sessions. Please go through that 2 sessions. I already given the most important questions on power electronics for BARC point of view. I already taken marathon sessions. That's why I'm giving only formulas, important points only. Vishwajit, you please go through that sessions. That is there in YouTube class only. Yes? Is it okay? Vishwajit, you please go through that one. Yes, friends. Yes, this is the MOSFET and this is the IGBT. I am giving the IGBT, students. Please go through the symbol of IGBT also. This is the IGBT. Yes, friends. This is the gate. This is the collector. This is the emitter. This is the IGBT. Insulated gate bipolar transistor. This insulated gate bipolar transistor, students. We know that IGBT is the combination of BJT plus MOSFET. BJT plus MOSFET. Students, the BJT plus MOSFET whose input characteristics are similar to MOSFET. whose output characteristics are similar to BJT. That's why it is a BJT plus MOSFET. All these devices having the same characteristics. All these devices having the same characteristics. Come on students. Yeah, this is I and this is minus I. This is V and this is minus V. Can anybody, what is the characteristics of this one? It blocks the forward voltage. It allows the only forward current. All these devices, students. That's why these are the example of each one, students. These are the example of each one. Come on, students. It is the example of unipolarity. It blocking only one polarity. Unipolarity and unidirectional device. Unidirectional device. Unipolarity and a unidirectional device, students. Come on, students. The next one is very important. The fourth one also. We may expect the questions like this. Draw the ideal characteristics of these devices also. This I am giving BJT. Come on, students. Yes, we can expect this like this also. This is the BJT. Yes, with anti-parallel diode. With anti-parallel diode, students. BJT with anti-parallel diode. And we may expect question based on MOSFET with anti-parallel diode. MOSFET with anti-parallel diode. This also we can expect, students. I am giving with anti-parallel diode combination. And we may expect the question with IGBT with anti-parallel diode. Yes, friends, with anti-parallel diode. And we may expect, yes, friends, a thyristor with anti-parallel diode. A thyristor with anti-parallel diode is called RCT. It is a reverse conducting thyristor. It is a RCT, students. It is a RCT. All these devices are called composite switches. All these devices are called composite switches. All these devices are having the same characteristics. All these are having the same characteristics, students. With anti-parallel diode. With anti-parallel diode, students. All these are having the same characteristics. Then what are the characteristics of these switches? What are the characteristics of these switches? Very good, Amita. That is operate in the first quadrant. This one is operate in the first quadrant. Now I am asking this one. All these devices are having which characteristics, students? Come on. All these devices are having the same characteristics. Okay, this is I and this is minus I. This is V and this is minus V, students. We can easy to remember. Simply remember, all these are the first quadrant, students. Actually, these are the first quadrant. Actually, these are operate in the first quadrant, transistors. But with anti-parallel diode, we also get the reverse current. We also get the reverse current. Because of anti-parallel combination, we can also get the reverse current. These are more useful. These devices are used in which application, students? In which case we can use this one? These are used in, very important, a transistor with anti-parallel combination. These are used in voltage source inverters. These are used in VSI, students, voltage source inverter. Because voltage source inverter must requires bidirectional capability. Bidirectional capability. Because it is conducting both the direction. That's why you can use in VSI. And these are the example of which one, students? These are the example of which one? Unipolarity bidirectional. Unipolarity bidirectional devices. Unipolarity bidirectional devices. Unipolarity bidirectional devices. RCT stands for reverse conducting thyristor, students. Unipolarity bidirectional devices. RCT stands for reverse conducting thyristor, students. One important question here. What is the advantage of placing the anti-parallel device? Anti-parallel diode. Because of anti-parallel diode, the turn-off time will reduce us. Across any device, if you place the anti-parallel device, the turn-off time is reduced, students, but turn-off power losses are increases. Turn-off time reduces, but turn-off power losses is increases. Next, one more very important, the fifth one I am giving, students. We may expect draw the ideal characteristics of these type of devices also. Instead of anti-parallel device, we may expect series diode. Series diode. This is BJT with series diode. Yes, friends. MOSFET with series diode. We may expect a MOSFET with series diode. Yes, friends. IGBT with series diode. IGBT with series diode also we can expect. Then in this case, then what type of characteristics we can get, students? We know that all these devices without any series diodes, it is operated in which quadrant? Without any series diode, it operates in which quadrant, students? First quadrant. This is I and this is minus I and this is V and this is minus V. Without any series diode, it operates in the first quadrant. But because of this series diode, it blocks the extra voltage, reverse voltage. That's why these are the which devices, students? This is a bipolarity. Bipolarity. Previous one is unipolarity bidirectional devices. But this is bipolarity and unidirectional devices. Unidirectional device. Because both the polarity, positive voltage it can blocks, negative voltage it can blocks. Positive voltage it can blocks, negative voltage it can blocks. Then it is used in, these are used in CSI. Because in current source inverter, bidirectional polarity is required. Bipolarity is required. That's why these are used in CSI. These are used in CSI. Both the blocking capacity is required for CSI. That's why these are used in current source inverter, students. These are used in current source inverter. Yeah, this is one important model of question we can expect based on the fundamental. Based on the fundamental, students. This also you remember. Come on, students. Yeah. One more that I am giving. Yes, students. The sixth one. Sometimes we may expect like this. This is the BJT. This is the BJT with series diode and anti-parallel diode. If the series diode and anti-parallel diode, students, if both series diode and anti-parallel diode is given, then first you check the condition for this diode is conducting or not. Yes, there is a path for conduction of this device. That's why there is a path. If it is combination is given, there is no significance for this diode. Once there is no significance for that diode, it is similar to anti-parallel diode. It is similar to anti-parallel diode. This is I, this is minus I, this is V and this is minus V. It is similar to anti-parallel diode means with respect to anti-parallel diode. Yes, students, with respect to anti-parallel diode, it is operate in the first quadrant, but extra which current it can allows? Reverse current it can allows. Yeah, this is the example. Yes, students. Yeah, that I given Viswajit. This is the MOSFET in series with it is operated extra we can. Without this series diode, MOSFET is operated in the first quadrant. But extra because of series diode, we know that diode is also blocks which voltage? Reverse voltage. Diode is also blocks the reverse voltage, students. Yes. Is it okay, students? The next one. Students, detailed concept I am not going to explaining here because for time being I want to give all the formulas only that I am giving. List out. Yes, students. The next one is you concentrate 1 or 2 points with respect to power diode. With respect to power diode. All these are the fundamental, students. In power diode, which points mainly you remember? It is how many layers, students? It is a 3 layer. It is a 3 layer. It is a 3 layer. 2 terminal. 2 terminal. 1 junction. 1 junction. All the diodes are unstable device. Unstable device. All the diodes are the unstable devices. That is not unstable. You can take the uncontrolled devices. Uncontrolled devices. All the diode family is the uncontrolled devices. But the point extra what you want to remember here? What you want to remember here, students? It is a 3 layer, not the 2 layer. But normal diode is 2 layer. But it's specially mentioned that it's a power diode. Power diode means you take the 3 layer, students. That extra there is an intrinsic layer. That extra is n minus layer. Intrinsic layer is distributed between the p plus and the n plus layer, students. Due to intrinsic layer, Due to intrinsic layer. What happens, students? Due to intrinsic layer, what is the advantage? Due to intrinsic layer, blocking voltage capabilities increases. Blocking voltage capability. Blocking voltage capability. That is the reverse blocking voltage capability. That is the reverse voltage blocking capability. Yes, friends, this is the reverse voltage blocking capabilities increases. Due to intrinsic layer. Intrinsic layer means N minus layer. N minus layer, reverse voltage blocking capabilities increases. Reverse voltage blocking capabilities increases. Voltage blocking capability is increases, students. Very important point. Capability increases. Due to an intrinsic layer, reverse voltage blocking capability increases. Yes. One more point, students. Power diode offers the less power loss due to conductivity modulation. Power diode, come on students, offers less power loss due to conductivity modulation. Due to conductivity modulation. Yes, come on students, due to conductivity modulation, it offers the less power loss. Less power loss. Next, one more point, students. Due to vertical structure, due to conductivity modulation, the power diode offers less power loss due to conductivity modulation. Not only due to conductivity modulation, due to vertical structure of the power diode, due to vertical structure of the power diode also, yes students, it offers the less power loss. That point also you remember. Yes. One more very important formula, students. In the case of power diode, the reverse recovery time equal to, how to find the reverse recovery time? The reverse recovery time equal to reverse recovery time. Reverse recovery time. Yes, friends. TRR equal to TA plus TB. TA plus TB. The TRR equal to reverse recovery time, students. What is TA? Time taken to remove charge carriers in layers. Time taken to remove charge carriers in layers. To remove charge carriers in layers. Charge carriers in layers. Yes, friends. What is the TB, students? Time taken to remove charge carriers in junction. Time taken to remove charge carriers at junction. To remove minority charge carriers, students. To remove charge carriers at junction. Charge carriers at junction. That is called TB. This total combination is nothing but a reverse recovery time. Come on, students. This total combination is nothing but a reverse recovery time. Yes, students. Yes, Manikandan. In BYJU'S app, recorded classes are stuck many times while watching. Okay, that problem will be resolved. Okay, if there is any problem, I will intimate. Okay, Manikandan. That I will intimate. Yes, Rajati, or please provide PDF of this one. Yes, I will share this PDF in my Telegram channel. Please go through that. Yes, Srikant, good afternoon. Srikant, good afternoon. Welcome to the session. Yes, friends. Yes, friends. The time taken to remove charge carriers in layers. This is the time taken to remove charge carriers at the junction. Yes, friends. Then you can define one factor here, softness factor. Softness factor. For diode, what is the softness factor of a diode? Softness factor of diode. This S is defined as TB by TA, students. What is TB? What is TA? That you know. This is called softness factor. If S less than 1, if S is less than or equal to 1, that diodes are called fast to recovery. Fast to recovery. Very important point, students. Fast to recovery or snappy recovery snappy recovery, yes friends, or abrupt recovery, yes friends, or transient recovery diodes, or transient recovery diodes, transient recovery diodes. Yes friends, this is the name. Question may be expect like this. For fast recovery diodes, what is the softness factor? If SC is greater than 1, then these are called, yes friends, slow recovery diodes, soft to recovery, or slow recovery diodes, Yeah, this you remember students with respect to diodes point of. And one more very important formula, yes students, the peak value of reverse current, peak value of reverse recovery current, peak value of reverse recovery current, yes friends, the peak value of reverse recovery current is IRM equal to TA into di by dt. This is the exact formula students, exact, this is exact. But if the data is available to calculate TA, use this formula to calculate IRM. But this IRM is also is nearly equal to TRR into di by dt. This is approximate. Based on the data available students. If the data is available to calculate TA, then use this IRM. If data is not there, then use this formula. IRM equal to TRR into di by dt. Next, reverse recovery charge. What is the reverse recovery charge students? The reverse recovery charge equal to QRR equal to, yes friends, 1 by 2 IRM, 1 by 2 IRM into, yes friends, TRR, 1 by 2 IRM into TRR. This is one formula. This reverse recovery charge QRR equal to 1 by 2 IRM into TRR. This is one formula students. One more formula for reverse recovery charge. Or QRR is also written as 1 by 2, yes friends, QRR is also written as 1 by 2 yes friends, di by dt into TRR square, This is one more formula for reverse recovery charge. These formulas are very important with respect to diode, students. And one important point you concentrate, Schottky diode. Schottky diode concept is also important students. With respect to Schottky diodes, which points you want to remember? This is the combination of metal plus semiconductor layer, aluminum plus N layer. That is, it is a combination of, this is the anode and this is the cathode. It's a metal plus semiconductor students. It is a metal plus semiconductor layers. This is the combination of metal plus semiconductor layer. Very important. Yes friends. And one more point to remember, it is a majority carrier device. Total conductivity is due to only electrons. Total conductivity is due to only electrons. Is due to only electrons. Yes friends. It is a majority carrier device. Can anybody tell another example for majority carrier device? Can anybody tell any another example for majority carrier device, friends? Schottky diode is the example of majority carrier device. Yes, friends. Can anybody tell another example for majority carrier device? The one more example for majority carrier device is MOSFET. MOSFET is also majority carrier device. SIT is also majority carrier device. This is also example of majority carrier devices, students. It is a majority carrier device. MOSFET is also majority carrier device. SIT is also majority carrier device. Students. Yeah, this you remember. Yes, with respect to Schottky diode, this we can remember. Yes, friends, with respect to frequency of operation, with respect to power application, with respect to power application, with respect to power application, students, among all the diodes, which diode is used for high power application? General purpose diode is used for high power application. General purpose diodes. The next one is fast recovery diodes. Fast recovery diodes. General purpose diodes, fast recovery diodes. The third one is we can use general purpose diodes, fast recovery diodes. Next, yes friends, Schottky diodes. Schottky diodes. Then least power application is silicon carbide diodes. Silicon carbide diodes. With respect to frequency of operation. With respect to frequency of operation, students. Then high frequency silicon carbide diode. Silicon, SCD, silicon carbide diodes are used for ultra high frequency application. Ultra high frequency, students. Ultra high frequency. The next one is Schottky diode. The next one is fast recovery diodes. Least frequency application is general purpose diodes. Least frequency application is general purpose diodes. These general purpose diodes are used for at power frequency application. At power frequency. These are used for at power frequency, students. This Schottky diodes. This is the Schottky diodes. This is the Schottky diode. The Schottky diodes are used for high frequency, low voltage. Very important. High frequency and low voltage application we can use, students. These fast recovery diodes are used for low turn off time application. Low turn off time applications. For low turn off time applications, we can use the fast recovery diodes. Okay, this comparison is also important to answer simple theory questions, students. Yeah, all these points you remember with respect to which one, students? Diodes. With respect to diodes, these points you remember, students. With respect to diodes. Now I am starting the one more important device, very important for competitive exam, that is the SCR, students. SCR. That I am explaining what the important points with respect to thyristor. SCR or thyristor, students. Okay, SCR or thyristor. Yes, I think all of you know this one. A thyristor is the combination of yes friends, a thyristor is the combination of thyraton plus transistor. It is the combination of thyraton plus transistor. That is, its principle is similar to thyraton. Its principle is same that of thyraton. Yes friends, it is the thyraton plus transistor. And construction is similar to transistor. It is a thyraton plus transistor. Yes, thyristor is thyraton plus transistor. Its principle is same that of thyraton. Its principle is same that of thyraton, students. Its principle is same that of thyraton. Its construction is similar to transistor. That's why it is the combination of thyraton plus transistor. Yes, Vishwajit. What's your doubt? MOSFET. What's your doubt? It is a combination of thyraton plus transistor, friends. Thyraton plus transistor. Yes. Yes, friends. Very important points. Please concentrate. For example, we know that SCR is having how many layers, students? SCR is having how many layers? It's a 4 layer. P1, N1, P2, N2. This is anode and this is cathode. Gate is always connected to inner P layer nearer to J2 junction. This is J1, this is J2, this is J3. Yes, friends, it is how many layers? 4 layer, 3 terminal. Yes, friends, come on. 4 layer, 3 terminal. How many junctions? 3 terminal, 3 junction. Bistable means 2 states. Even diode is also bistable. Bistable, yes, friends. Semi-controlled Positive feedback device. Positive feedback device. Internally within the SCR, a positive feedback takes place. Yes, friends. Because of this only, the SCR will turn on. Internally within the SCR, which feedback action takes place? A positive feedback action takes place, friends. Internally within the SCR, a positive feedback action takes place. It is a 4-layer, 3-terminal, 3-junction, bistable, semi-controlled positive feedback device, students. Positive feedback device. Come on, students. Come on. A bistable, semi-controlled positive feedback device. Positive feedback device. Yes, friends. Yes. We know this one. For example, the questions may be expected like this. This is the SCR, students. This is P1, N1, P2, N2. P1, N1, P2, N2. This is anode and this is the cathode and this is the gate. So anode is connected to positive plate, cathode is connected to negative plate. This type of questions also we can expect. J1, J2, J3 students. Now tell me, students, this is under which mode? Forward blocking mode. This is under which mode, students? Forward blocking mode. Forward blocking mode. Now, if the SCR is under forward blocking mode, which junctions are forward bias? J1, J3 is forward bias. J2 is reverse bias. This type of questions also we can expect, students. If it is connected like this, this is the SCR with 4 layers. SCR with 4 layers, friends. This P1, N1, P2, N2. This is P1, this is N1, this is P2, this is N2. Yes, friends. And anode is connected to negative plate, cathode is connected to positive plate. This anode connected to negative plate, cathode is connected to positive plate. This is under reverse blocking mode. Reverse blocking mode. Come on, students, important points. Reverse blocking mode. In reverse blocking mode, J1, J3 is which one, students? This J1, J3 is reverse bias. J2 is forward bias. J2 is forward bias. This notation, whatever I given, according to that notation, I am telling that. But simply you remember, in forward blocking mode, outer junctions are forward bias, inner junction is reverse bias. In reverse blocking mode, outer junctions are reverse bias, inner junction is forward bias, students. Inner junction is forward bias. Yeah, these points also you remember, students. If the SCR is conducting, if the SCR is conducting, if the SCR is conducting, yes, friends, all the junctions are forward bias. All 3 junctions are forward bias. Very important points. All 3 junctions are forward bias. Are forward bias. Yes, friends. Next, if once the SCR starts the conduction, once the SCR starts the conduction, once the SCR starts the conduction, yes, friends, when the SCR starts the conduction, by using gate, we cannot control the anode current. We cannot control the anode current. That is, anode current remains same. We cannot control the anode current. Based on these statements, I already solved the problems also, students. Please go through that previous sessions. Yeah, once the SCR starts the conduction, by using gate, we cannot control the anode current, students. Next, very important, latching current, IL, is always greater than the holding current. Very important, students. The latching current is equal to 2 to 3 times of holding current. In average, latching current is equal to 2.5 times of holding current. From any relation, we can expect the question. Where IL is the latching current. IL is the latching current, students. Come on. IH is the holding current. IH is the holding current. Yes, friends. IH is the holding current. Always the latching current is greater than the holding current. And one more point to remember, latching current is associated with the turn-on process. Holding current is associated with the turn-off process, students. Latching current is associated with the turn-on process. Holding current is associated with the turn-off process, students. Come on, students. Yeah, this is about the points, very important points. And one more important, so many times asking in competitive exams, based on this I already solved the questions also. Please go through that previous session, students. I taken already marathon sessions on the question solving. 2 sessions I taken on power electronics. Please go through that sessions. But here I am giving very important formula. Yes, students. For reliable turn on of thyristor, for reliable turn on of thyristor, for reliable turn on of thyristor, turn on of thyristor. Yes, students. For reliable turn on of thyristor, very important, students. For reliable turn on of thyristor, gate pulse width, gate pulse width, gate pulse width must be greater than or equal to turn on time. Gate must be connect up to turn on time. That is the for reliable turn on of the thyristor. If the question is asked for reliable turn on of thyristor, very important concept, students. For reliable turn on of thyristor, turn on of thyristor. If it is asked, what is minimum gate pulse width? What is minimum gate pulse width? If the question is asked like this, for this type of, what is the minimum gate pulse width? If the question is asked like this, students, then find in given circuit, what you can do, students? In given circuit, in given data or from given data, what you can do, students? Yes, from given data find, from given data, yes, friends, find T at IL. Okay, that gives the minimum gate pulse width. This gives the minimum gate pulse width. This concept we can apply, students. If any question is asked, what is the for reliable turn on of thyristor? What is the minimum gate pulse width? It is asked. Find the T at IL corresponding to latching current. That T gives the minimum gate pulse width. One more important point, students. Come on. We know that. What do you mean by turn on? The turn on is nothing but bringing the SCR from forward blocking mode to forward conduction mode. The process of bringing the SCR from forward blocking mode to forward conduction mode. What do you mean by turn off? Turn off is nothing but a forward conduction mode to forward blocking mode. It is not reverse blocking mode, students. Very important. The turn on is nothing but a bringing the SCR from forward blocking mode to forward conduction mode. Turn off is nothing but a forward conduction mode to forward blocking mode, students. Very important. But always, which time is greater? But always, which time is greater, students? Off time is greater or on time is greater? Can anybody? Always, which time is greater? Yes, friends. Always off time is greater than the on time. Always off time is greater than the on time, students. Yes, friends, all of you. Good afternoon. Welcome to the session, students. Yes. Always off time is greater than the on time. One more important point. Very important, students. For reliable turn off of thyristor. For reliable turn off of thyristor. Turn off of thyristor. For reliable turn off of thyristor, students. For reliable turn off of thyristor, always which time is greater? Circuit turn off time is greater than the device turn off time. Very important. TC is greater than the TQ, students. Very important 5 star. Where TC is the circuit turn off time. Circuit turn off time. Circuit turn off time, students. TQ is the device turn off time. Device turn off time. Come on, students. It is the device turn off time. TC is the circuit turn off time. TQ is the device turn off time, students. If safety factor is given, generally TC equal to some safety factor into TQ. Generally TC equal to some safety factor into TQ, students. What is SF? This is the safety factor. This is the safety factor, students. This is the safety. SF is the safety factor. If it is not visible, I am writing here. Where SF is the safety factor. This is also important formula. This is the safety factor. Yes, what the relation between the device turn-off time and circuit turn-off time, students? Very important. Yes, come on, students. One more very important observation here. What the circuit turn-off time? What the circuit turn-off time, students? It is the time taken a reverse voltage applied across the device. It is the time taken. It is the time taken a reverse voltage. A reverse voltage applied across the reverse voltage applied across the device. Applied across the device. Yeah, this is the device turn-off time. Is it is the time taken by the device to complete the turn-off process. That I am not giving. Device turn-off time is it is the time taken by the device to complete its turn-off process, students. Turn-off process. During device turn-off time itself, the anode current is reduced below the holding current. Not during TC time. During device turn-off time itself, the anode current is reduced below the holding current. That point you remember, students. Yes, friends, please concentrate. Whatever the points that I am giving, these are the very important points with respect to semiconductor devices. Mainly here I am giving the first, I am giving the semiconductor devices, students. With respect to semiconductor devices that I am explaining. Please concentrate, students. Please concentrate. Next. One more important, students. For example, this is the SCR. This is the SCR. Let SCR is under forward blocking mode. Across the SCR, if any capacitance is connected, let the current through this SCR is I. Let this SCR offers the capacitance of CT. That is the thyristor capacitance. Yes, friends, this SCR capacitance. We know that if the SCR is under forward blocking mode, it is equivalent to capacitor. If the SCR is under forward blocking mode, it is equivalent to capacitor. Then in this case, then how to define I equal to, students? Yes. Yes, friends. Yes. It is the capacitance offered by the thyristor. Across this thyristor, we are connected one capacitor. Students. Then, yes, friends, I equal to C equivalent into dV by dt. From this formula also we can expect the question. I equal to C equivalent into dV by dt. What is C equivalent here? The C equivalent equal to C plus CT. This is the capacitance connected across the SCR. That CT is the thyristor capacitance. If the thyristor is under forward blocking mode. Students. Yes, friends. One more point to remember here. The total turn-on time of SCR is students. The total turn-on time of SCR equal to delay time plus rise time plus spread time. Delay time plus rise time plus spread time. This is very important. This is the total turn-on time of SCR. Yes. Yes. One more important point, students. By controlling gate current, only delay time is controlled. Yes, friends. But rise time and spread time is unaffected. Rise time and spread time is unaffected. By controlling, this is, we know that T on equal to TD plus TR plus TS. This is delay time. This is rise time. This is rise time. This is the spread time. This is the spread time. Yes, students, if IC is increases, TD is reduces and TN is also reduces. But TR and TS unaffected. TR and TS is unaffected. Okay, these points you remember, students. Yes, all these points I am giving with respect to semiconductor devices. With respect to SCR, I am explaining, students. Next, I think all of you know this one. Yes. In SCR gate characteristics, students. In SCR gate characteristics. In SCR gate characteristics. In DC triggering of SCR. In DC triggering of SCR. In DC triggering of SCR. What the average power loss? The average power loss equal to VC into IC. This is equal to maximum power loss. Maximum gate power loss. The average gate power loss equal to maximum gate power loss, students. In DC triggering of SCR, the average gate power loss. The average gate power loss is equal to maximum gate power loss. In DC triggering of SCR, students, the average gate power loss equal to maximum gate power loss. Yes. In pulse triggering of SCR. In pulse triggering of SCR. Come on, students. In pulse triggering of SCR. In pulse triggering of SCR. Come on, students. In pulse triggering of SCR. What is the PGAV? PGAV is the average gate power loss. What is the PGAV, students? Can anybody? The average gate power loss equal to VG into IC into T on by T. This is equal to VG into IC into T on into F. T on into F, students. Yes, this is also equal. This is one important relation. Very important relations. The average gate power loss equal to this one. VG IC into T on by T, that is VG IC into T on into F, students. And you also write the average gate power loss equal to yes PGM into delta, or you can also write like this VG IC into delta. VG IC into delta, but this VG IC taken as a PGM. This is a PGM into delta. This is one more important formula for average gate power loss. Then what is the delta here, students? This delta is the duty cycle. This the delta is the duty cycle or duty ratio or duty ratio. Duty cycle or duty ratio, students. The delta is the duty cycle or duty ratio. How to write delta equal to T on by T? Then what is the T on, students? Delta T, very important. What is the T of, students? Very important formulas. 1 minus delta into T. Then what is the on time by off time? This on time by off time is called Mark II space ratio. This on time by off time is called Mark II space ratio. What is the Mark II space ratio, students? That is the on time by off time. This we can get delta by 1 minus delta. What is the on time by off time? This is equal to delta by 1 minus delta, students. This is equal to delta by 1 minus delta. Very important formula to please concentrate. What is the Mark II space ratio? The Mark II space ratio equal to delta by 1 minus delta. Yes, students. Please concentrate. Yes. One more important with respect to gate characteristics of SCR. With respect to gate characteristics of SCR, students. Yes. For example, this is the gate triggering circuit. This is the gate triggering circuit. This is the gate triggering circuit. Yes, friends. This is the gate source resistance. Yes, gate source resistance. And this is the gate source voltage. This is Vs. And this is IC is the gate current. Vg is the gate voltage. Rs is the gate source resistance. Rs is the gate source resistance. Okay, this is the SCR. This SCR is supplied with forward blocking voltage. Now in this case, what are the relation, students? This Vs equal to Vg plus Ig into Rs. Vs equal to Vg plus Ig into Rs, students. This Vs is gate source voltage. Gate source voltage. Come on, students. This is the gate trigger voltage. Actual gate voltage we are applying for gate. There is a gate trigger voltage. Gate trigger voltage. What is this Ig, students? It's a gate trigger current. It's a gate trigger current. It's a gate trigger current. Yeah, this Vs equal to Vc plus Ic into Rs. What is the Rs? Rs is the gate source resistance. Gate source resistance. Come on, students. This is the gate source resistance. Okay. Now, for example, if any resistance is connected across gate to cathode terminal, if Rg is connected, if it is given like this, if any resistance, in this case, students, here I am giving this SCR is across gate to cathode terminal if any resistance is connected. Yeah, this is the SCR. Yes, students. Across this gate to cathode terminal if any resistance is connected. And this is the Rs. And this is the Vs. Vs is the source voltage. That is the gate source voltage. And this is, but always Ig is fixed. And this voltage is Vg. Let this R is connected. Let the current through this R is IR. Now tell the students. Now how we can write? Now let this current is Is. This current is Is. Now this Is equal to Ig plus IR. What is IR? This IR equal to Vg by R. Like this you can simplify. Then we can apply KVL here. What the KVL? Vs equal to Is into Rs plus Vg. That means if there is no resistance across gate to cathode terminal, this current and this current is same. If the resistance is connected across gate to cathode terminal, this current and this current is different. But always the gate current you take Ig only. Always you take the gate current is Ig only, students. Then Vs equal to Is into Rs plus Vg you can take. Yeah, this is the design of gate triggering circuit. These formulas you can take, students. Very important. Yes. One more very important formula with respect to gate characteristics. If Ig is increases, I told already turn on time is reduces. But generally, high frequency pulse triggering is more preferable. To reduce the turn on time, yes friends, to reduce the turn on time, high amplitude, high frequency, narrow pulse width, yes friends, rectangular pulses are more preferable. Rectangular gate pulses are more preferable. More preferable, students. This is very important. Rectangular gate pulses are more preferable. That means instead of low frequency pulse triggering, you can use the high frequency pulse triggering. High frequency pulse triggering is having high amplitude, narrow pulse width, then turn on time will be reduced. But one more advantage is there, friends. Due to high frequency pulse triggering, yes friends, high frequency pulse triggering, then one is size of the pulse transformer is reduced. The another advantage is turn on time is reduced. But if both are there in option, both A and B is there, then you can select both A and B. But that option is there, you give the preference to size of the pulse transformer will be reduced. That is the main preference, students. Yes. A pulse transformer core is made with which material, students? Come on. The pulse transformer core is made with which material? Can anybody? Made with ferrite. Ferrite. To reduce hysteresis and eddy current losses at high frequency. To reduce WH and WE hysteresis and eddy current losses. Yes, students, at high frequency. That's why the pulse transformer core is made with the ferrite core. Yes, friends. What is the turns ratio of pulse transformer? The turns ratio of pulse transformer is can anybody, students? The turns ratio of pulse transformer or isolation transformer is 1:1 or 1:1, 1:1:1 or 2:1:1. Any option we can expect, students. This is without center tapped arrangement. This is with center tapped arrangement. This is the turns ratio of the pulse transformer, students. The turns ratio of pulse transformer is 1:1 or 1:1:1 or 2:1:1. This is with center tapped and this is the without center tapped arrangement. In gate characteristics of SCR, yes, friends, the slope of the load line indicates. Can anybody? What is the slope of the load line indicates, students? The slope of the load line indicates which one? Gate source resistance. The slope of the load line indicates gate source resistance. Yes, friends. Practically, gate characteristics are non-linear. Gate characteristics are non-linear, students. Gate characteristics are non-linear. It's the gate characteristics are non-linear. If ideally the slope of gate characteristics equal to the slope of gate characteristics. If the condition is given ideal, students, the slope of gate characteristics equal to Vz by Ic. This we can use in solving of the problems. The slope of the gate characteristics equal to, very good, Rajat. Yes, the practical gate characteristics are non-linear. Ideally, the slope of gate characteristics is Vz by Ic. In gate characteristics of SCR, the slope of the load line indicates gate source resistance. Very good. Yes. Yeah, these are the points you remember with respect to gate characteristics. And all these points with respect to SCR, students. All these points I am explaining with respect to SCR. In a protection circuit of SCR, students, for example, an inductor is connected in series with thyristor. This we can use for di by dt protection. This inductor is connected in series with SCR. This is used for di by dt protection. For di by dt protection of SCR, we can use protection of SCR. An inductor is connected in series with thyristor, students. This is also called Hrs number circuit. For di by dt protection, we can use this one. This is also called Hrs number circuit, students. Yes. An inductor is connected in series with SCR for di by dt protection, students. This is also called Hrs number circuit. For dv by dt, but generally, what the range of di by dt? Range of di by dt, students, 20 to 300 amperes per microsecond. Very important. If the question is asked, what the range of di by dt, students? The range of di by dt is 20 to 300 amperes. It's a 20 to 500, not 300, students. It's a 20 to 500 amperes per microsecond. This is the 20 to 500 amperes per microsecond. Yeah, Shashidhar, yeah, I will plan. Utilization of electrical energy also I will plan. Yes, Shashidhar. Yes, friends, all of you welcome to the session. Please like the session and share the session. Who are preparing for, yes, for time being, I'm not covering the total power electronics. Actually, I tried to plan for to complete within 2 hours total power electronics, but it's somewhat difficult. But mainly today's session, mainly I'm concentrating on the devices that I'm explaining. Yes. The range of di by dt is 20 to 500 amperes per microsecond. The range of di by dt is 20 to 500 amperes per microsecond. Yes, friends. For example, a thyristor across this resistance and capacitor. This is called snubber circuit. This is called snubber circuit. A resistance and a capacitor, and we also connect one diode across the resistor. This is the actual snubber circuit. This is called snubber circuit, students. This is called snubber circuit. This di by dt production means to reduce the di by dt. Di by dt production means to reduce di by dt, not for eliminate. To reduce or suppress the di by dt. To reduce the di by dt, students. We cannot eliminate. Snubber circuit. It reduces dV by dt for dV by dt production. For dV by dt production, we can use the snubber circuit. Yes, that is a snubber circuit reduces dV by dt, not eliminates the dV by dt. Reduces or suppress the dV by dt. Suppress the dV by dt. It suppress the dV by dt, friends. Suppress means the meaning of suppress is nothing but snub is nothing but a suppress. Snub is nothing but a suppress. That's the reason why it is called snubber circuit. That's the reason why it is called snubber circuit. A resistor limits the discharging current of capacitor. It limits discharging current of capacitor. Discharging current of capacitor. Current of capacitor. What is the purpose of using diode? A diode bypass the resistor. A diode bypass the resistor. Bypass the resistor. Yes, friends. A diode bypass the resistor during discharging. Yes, during charging of the capacitor. During charging of the capacitor. During charging of capacitor. Yeah, that is the purpose of using the diode. Generally, a snubber circuit with diode is called polarized snubber. A snubber circuit without diode is called, yes, a polarized a snubber circuit without diode is called unpolarized snubber circuit. Unpolarized snubber circuit. Polarized means with diode. Without diode, unpolarized student. But generally in SCR, unpolarized snubber circuits are preferred. But in the case of BJT and MOSFET and ICPT, in that application, we can use the polarized snubber circuit. Generally in the SCR, unpolarized we can use. But in BJT, MOSFET and ICPT, we can use the polarized snubber circuit, students. Okay, that points also you remember. Yes. Then what are snubber circuit parameters? A design of snubber circuit parameters. This is important formulas to solve the problems. Design of snubber circuit parameters. Yes, friends. Snubber circuit parameters. Yes, friends, please concentrate. How to design the design of snubber circuit parameters. Yes, friends. With respect to design of snubber circuit parameters, please concentrate. This is the circuit I am drawing. This is very important formulas to solve the problems based on the snubber circuit. Yes. Shashidhar and drives also. Yes, yes. I will plan the sessions. Shashidhar, I will plan the sessions. Yes, are you preparing for which exam? Shashidhar, you are preparing for which exam? Yes. Yes, friends. This is, I am explaining for design of snubber circuit parameters. These formulas are very important to solve the problems on snubber circuit. Let Vs is the supply voltage. Yes, friends. This is L. Across this, I am connecting the resistance and capacitance. This is the snubber circuit resistance. CS is the snubber circuit capacitance. RL is the load resistance. Yes, RL is the load resistance. One formula you remember, V equal to L into, come on students, this V equal to L into di by dt. Then from this, we can calculate L equal to V by di by dt. This is the design of snubber circuit parameter, students. Next, one more formula you concentrate. Come on students. IC equal to C into CS into dV by dt. Using this formula, you can calculate snubber circuit capacitance. Yes. One more formula, students. Yes. Please concentrate. One more formula. This is dV by dt equal to, yes, dV by dt equal to, yes, students, this is Rs into di by dt. From this we can design what is the Rs. Then one more formula. For design of snubber circuit capacitance, we can also use Cs equal to 2 zeta by Rs plus RL whole square into L. Yes, the snubber circuit capacitance we can design using this formula or this formula based on the given data. Cs equal to 2 zeta by Rs plus RL whole square into L, students. Okay, where zeta is the damping ratio. Zeta equal to damping ratio. Generally, in the case of snubber circuit, we can take 0.5 to 1. If zeta is not given, take zeta equal to 0.5 for best results. If zeta not given, yes friends, if it is not given, take zeta equal to 0.5. By taking the zeta equal to 0.5, you can design the snubber circuit parameter, students. But generally, these formulas are very important to solve any problem based on the snubber circuit. And if here I given this formula for DC supply, students. Sometimes if the supply is AC, then replace, take Vs by Vm. Replace Vs by Vm. Instead of Vs, you substitute the maximum value of the supply. Maximum value of the supply you can substitute, students. Okay, that is the points to remember. If the supply is AC, then which one you can take? Replace the Vs by Vm. Yes, students. Rajati, mainly for time, actually it is a 2-hour session. That's why mainly I am concentrating the devices. Different models of question based on the choppers, inverters, AC voltage controllers, cyclo converters. I already taken the sessions in BARC for BARC exam itself. Rajati, if you want that sessions, please go through the same YouTube channel, or if you want link for that one, I will share in my Telegram channel. Please go through that one. Yes, for time being, it is a 2-hour session. It's not completing all the formulas. That's why mainly I am concentrating only on the devices for today's session. Yes, if you want remaining questions that I solved, yes, you please go through that. Yes, friends. One more important concept with respect to SCR, students. Heating and cooling circuit of SCR. Heating and cooling circuit. Cooling circuit of, yes, sir. Heating and cooling circuit of, yes, SCR. Not only for SCR, this also applicable for BJT, MOSFET, IGBT, etc. For all the semiconductor devices, this concept is applicable. Very important, student. Heating and cooling circuit of SCR. Yes, friends, heating and cooling circuit. With respect to heating and cooling circuit of SCR, yeah, that you concentrate, students. That you concentrate. Then, this you remember, students, very important. The average power loss equal to, this is the average power loss. The average power loss equal to, here I am drawing the heating and cooling circuit. From this I will give the formulas, that is very important. The average power loss equal to, yes, this is theta JC. Please concentrate. Here clearly I am drawing. Yes, friends. Here this is the average power loss. This is theta JC. And this is junction This is a junction temperature is Tj. It is a casing temperature is Tc. Sink temperature is Ts. Ambient temperature is Ta. Yes friends, ambient temperature is Ta. Very important formulas. This is theta Jc. This is theta Cs. This is theta Sa. Yes friends, this theta Jc, theta Cs, theta Sa is which resistances? Thermal resistances. Thermal resistances. Very important. Thermal resistances. What are the units of thermal resistances? What are the units of thermal resistance, students? Degree centigrade per watt or degree centigrade per joules per second. Degree centigrade per joules per second, students. Or we can also use Kelvin per watt or Kelvin per joules per second. This also we can use. Yes. Now we can write. We can define from junction to ambient. We can define from junction to casing. For example, I am defining average thermal power, students. Yes, students. Yes, come on, students. What is the average thermal power? Tj to junction to casing. That is Tj minus Tc by theta Jc. This also equal to Ts minus Tc by, it is a casing, this is the sink, this is the ambient. Tc minus Ts by theta Sa. It is also equal to Ta minus Ts minus Ta by theta Sa. Yes friends, we can also write the formula. For example, I want to define from junction to sink. Junction to sink. Then how to define junction to sink? Tj minus Ts by from junction to sink. What is the resistance? This is a thermal resistance. Theta Jc plus theta Cs, students. Theta Jc plus theta Cs. Clear, students? For example, I want to define from, come on students, junction to ambient. Junction to ambient. You can write any formula. Tj minus Ta by, what the junction to ambient? Total resistance we can add. Theta Jc plus theta Cs plus theta Sa. Where theta Jc plus theta Cs plus theta Sa equal to theta T. That is the total thermal resistance, students. It is the total thermal resistance. Theta Jc means junction to casing resistance, thermal resistance. Theta Cs means casing to sink thermal resistance. Theta Sa means sink to ambient thermal resistance, students. Very important, very important. What is the Tj? Tj is the junction temperature. Junction temperature, students. What is the Ts? Ts is the sink temperature. Sink, that is heat sink temperature. Heat sink temperature. Tc is casing temperature. Casing temperature. Yes, friends. What the Ta? Ta is the ambient temperature. The ambient is, that is environment. Ambient temperature. This terminology also you remember, students. This is the very important formula. You please concentrate these formulas to answer any question based on the heating and cooling circuit of SCR. Based on the heating and cooling circuit of SCR, students. This is the average thermal power. Yes, these points mainly you remember, students. Generally, these heat sinks are made with which material, students? Heat sinks are made with either copper or aluminum, but aluminum is more economical. Very important. Heat sinks are made with which material? Yes, friends. Heat sinks are made with copper or aluminum. Copper or aluminum, but aluminum is more economical. But in economical point of view, aluminum is more favorable. But aluminum is more economical. More economical, students. That's why in economical point of view, aluminum is preferable. Yes, students. Here I given what is the di by dt production and what is the dv by dt production. Generally, the range of dv by dt, students. If you take range of dv by dt, then 20 to 500 volts per microsecond. 20 to 500 volts per microsecond. And one more point to remember, for over voltage production, what you can use, students? Thyrector or varistor, metal oxide varistor, MOV, metal oxide varistor or non-linear resistor is used. MOV or non-linear resistor is used. Non-linear resistor is used. Yes, friends. Okay, this point also you remember. For overcurrent production, we can use the, here I am writing, students, for overcurrent production, what you can use, students? Instead of writing here, I will write the next slide. Better. Yes, friends. Okay, this I given. Here I am writing. For overcurrent production, we can use circuit breaker or FACLF fuse. For overcurrent production, what you can use, students? Circuit breaker or FACLF fuse are used. That is, fast acting current limiting fuses are used. Fast acting current limiting fuses. FACLF is used. Fast acting current limiting fuses are used. Yeah, these points you remember. Yeah, this is about with respect to production circuit and with respect to heating and cooling circuit. And one more very important formulas with respect to SCR, students, I want to explain with respect to series and parallel connection of SCR. Series and parallel connection of SCRs. Parallel connection of SCRs. Then what are the points you remember with respect to series and parallel connection of SCR, students? Which points you remember with respect to series and parallel connection of SCRs? Yes, come on, students. Yeah. This series connection is used to meet high voltage demand. This parallel connection is used to meet high current demand. Parallel connection is preferable. Yes, friends. Come on, students. Yeah. Then here I am explaining what is the string efficiency for series connection. For series connection, string efficiency equal to, what is the string efficiency for series connection, students? Eta equal to Vs by Ns into V1. Very important formula to solve the problems. What are the Vs, students? Total string voltage. High voltages are taken as string voltages. What is Ns here? Number of series connected SCRs. Come on, students. Series, very important formulas. Series connected SCRs. What is NP, students? Here NP is not there. Ns is the number of series connected SCRs. What is the V1, students? Individual voltage rating of single SCR. Individual voltage rating of single SCR. Yeah, this is the string efficiency for series connection. If you want percentage string efficiency, means into 100, students. If you want percentage string efficiency, the string efficiency into 100. Next, for parallel connection of SCRs, what is the string efficiency, students? The string efficiency eta equal to Is by Np into I1. The string efficiency eta equal to Is by Np into I1. If you want percentage string efficiency, this is into 100. What is Is, students? This Is is total string current. Come on, students. What is Is? Is is the total string current. Total string current. Where Np is the number of parallel connected SCRs. Number of parallel connected SCRs. Parallel connected SCRs. Yes, friends. This Np is the number of parallel connected SCRs. I1 is the individual current rating of single SCR. Individual current rating of single SCR. These formulas we can use, very important for compute point of view. Current rating of single SCR. Yes, friends. Once you know the string efficiency, then how to calculate derating factor? Very important, students, derating factor. The derating factor DRF equal to 1 minus string efficiency. DRF equal to 1 minus string efficiency. Yes, it indicates the reliability of the string. It indicates reliability of the string. Come on, students, reliability of the string. Yes, reliability of the string. A derating factor indicates the reliability of the string. Yes, one more important point, students, here. Come on. All these points I am giving with respect to devices. With respect to devices that I am explaining, students. Yes, derating factor equal to 1 minus string efficiency. It indicates the reliability of the string. To equalize the static characteristics. To equalize the static characteristics. Static characteristics of SCR. A static equalizing circuit is used. A static, yes friends, equalizing circuit is used. Equalizing circuit is used. Then what do you mean by static equalizing circuit? Across each SCR, one equal value of resistance is connected. Across each SCR, one equal value of resistance is connected, students. This is called static equalizing circuit. To equalize that static characteristics. Why you want to equalize the static characteristics? To equalize the voltage distribution. Why you want to equalize the voltage distribution? To equalize the voltage distribution, students. To get the more string efficiency. To get the more string efficiency. This is the static equalizing resistance. The static equalizing resistance R equal to, very important formula. What is the static equalizing resistance? The static equalizing resistance R equal to Ns into VBMX minus Vs by Ns minus 1 into delta IB. Yeah, this is the static equalizing resistance, students. To equalize the static characteristics. Ns is number of series connected SCRs. Number of series connected SCRs. Series connected SCRs. Yes, friends. What is VB max? Voltage across single SCR. Voltage across single SCR. Single SCR. That is the VB max. This delta IB equal to, students. Delta IB equal to IB max minus IB minimum. Minimum leakage current minus maximum leakage current minus minimum leakage current. This is the leakage current. Yes, friends. Leakage current. Yeah, this is the static equalizing resistance. The static equalizing resistance is used to equalize the static characteristics. To equalize the dynamic characteristics. To equalize the, yes friends, dynamic characteristics of SCR. Dynamic characteristics of SCR. What you can use, students? A dynamic equalizing circuit or snubber circuit is used. A dynamic equalizing circuit A dynamic equalizing circuit or snubber circuit is used. Equalizing circuit or snubber circuit is used. Snubber circuit is used. That means to equalize that means snubber circuit is not only for dV by dt production, it is also used to equalize the dynamic characteristics, students. Then what is the dynamic equalizing circuit? Yeah, this is the dynamic equalizing circuit, students. Very important. A dynamic equalizing circuit is same that of snubber circuit. It also consists of resistance and capacitance and resistance across the diode. Yes, that is a diode across the resistance, students. This is called dynamic equalizing circuit or snubber circuit. This is called dynamic equalizing circuit or snubber circuit. The purpose of diode I already given in the snubber circuit. Then what is this dynamic equalizing capacitance? The value of C equal to, yes, Ns minus 1 into delta Q by Ns into VBMX minus Vs. Yes, friends, Ns into VBMX minus Vs. Yeah, this is the dynamic equalizing capacitance. That circuit is dynamic. This is the dynamic equalizing capacitance. It is calculated based on the reverse recovery characteristics or turn-off characteristics of SCR. Dynamic equalizing capacitance. Very important formula, students. This is used to equalize the dynamic characteristics, where delta Q equal to charge difference. Remaining terms you know. Charge difference. But point to remember, students. Okay. Here I am telling that ideally string efficiency equal to 1. Ideally string efficiency equal to 1. But practically always string efficiency is less than 1. String efficiency is less than 1. Yeah, this is the points you remember with respect to, yes, students. All these points are with respect to SCR, students. Whatever I explained, all these points are with respect to SCR. Here I am giving with respect to frequency of operation, comparison of various types of devices. Come on, students. With respect to frequency of operation, which is used for high frequency. Very important comparison. MOSFET. Next one is IGBT. The next one is BJT. Next one is GTO. Next one is SCR. SCR is used only at power frequency. As compared to SCR, least frequency is which one, friends? As compared to SCR, least frequency is triac. Triac is used for very low frequency applications. Very low frequency applications we can use. That triac is 4-quadrant operation. In the ideal characteristics, if you draw the for triac, if you draw the ideal characteristics, actually I am not given this one. If you draw the ideal characteristics for triac, students, this is I, this is minus I, this is V, minus V. It is a anti-parallel connection of two thyristors. It is an anti-parallel connection of two thyristors. This is operated in the 4 quadrants. It is operated in the 4 quadrants. Yes, MOSFET, IGBT, BJT, least frequency is SCR, high frequency is MOSFET. In MOSFET again, N MOSFET is high frequency. N MOSFET is high frequency as compared to P MOSFET. As compared to P MOSFET, students. Yes, come on, students. Next, this is with respect to frequency. With respect to turn on and turn off times. Turn on time and turn off times. Turn on and turn off times. Yes, friends. With respect to turn on and turn off times, then which is high frequency means low turn on time. Exactly opposite. MOSFET is less than, IGBT is less than, BJT is less than, GTO is less than SCR. SCR is more turn on time and turn off time. Why? If on time and off time is more, T is more, frequency is less. That is the reason exactly opposite we can get, students. Then with respect to power application, which is used for high power application, students. SCR is high power. The next one is GTO. The next one is BJT. The next one is IGBT, which is the low power application MOSFET. MOSFET is used for low power and high frequency application. Yes, with respect to power loss, power application is different, power loss is different. With respect to power loss, which having the high power loss students? MOSFET is having the high power loss. The next one is, which is the high power loss students? IGBT. The next one is BJT. The next one is GTO. Which is the least power loss? Very important comparison students. SCR is the least power loss. SCR is used for low power loss students. Next. With respect to voltage drop. With respect to voltage drop. With respect to voltage drop students. Which is the high voltage drop? MOSFET is high voltage drop. The next one is IGBT. The next one is BJT. The next one is GTO. SCR is the least voltage drop. With respect to input impedance or input resistance. Very important comparison to answer theory question students. With respect to input resistance, MOSFET is high input resistance. In that MOSFET, P MOSFET is high input resistance students. Next IGBT. Next BJT. The next one is GTO. The next one is SCR. Yes. Yeah, these points you remember. The comparison of various types of devices students. Comparison of various types of devices. All these are the points with respect to devices students. Here one more point I am giving very important. In the concept of LC circuit students. In the concept of LC circuit. For example, if it is a thyristor or diode. If it is a thyristor or diode is given. If it is a LC circuit is given students. If the LC circuit is given. Okay, this is the VS. Yes, friends. This is L and this is the C. Let the initial current through the inductor is 0. Initial current through the capacitor is also 0. There is no initial current in the inductor. There is no. I am talking about initial voltage across the capacitor. With respect to capacitor means if you take the voltage. The initial voltage across the capacitor equal to 0. Then in this case, what the current in the LC circuit? I equal to Vs into square root of C by L into sine of 1 by root LC into T. Very important students. Very important. This is the I equal to Vs into square root of 1 by root LC into T. This also we can write. This is I equal to 0 to T equal to pi by 2, that pi root LC. I equal to max, I max, that equal to Vs into square root of C by L to T equal to, yes friends, pi by 2 root LC. Very important in the LC circuit concept. In LC circuit concept, it is very important students. You please concentrate. Compulsory we can expect the question. Compulsory we can expect the questions based on this concept of LC circuit students. Okay, with respect to commutation circuits point of view and with respect to choppers point of view also it is important. Okay, this is for initial current through the inductor is 0, initial voltage across the capacitor is 0, then we can apply this formula students. Yes friends, come on. Yes students. Yes. Then what the peak voltage across the capacitor? The peak voltage across the capacitor is 2 Vs in this case. What is the conduction? What is the conduction time of SCR? Conduction time of SCR is pi root LC. Conduction time of SCR is pi root LC. This you remember students. It is a pi root LC. That is the conduction time of SCR. For example, if IL of 0 equal to 0, VC of 0 equal to minus V0. That is the negative voltage. That is the negative voltage. That the initial voltage across the capacitor is negative. Then how you can take I equal to? If it is negative voltage is given, you take this is plus students. Vs plus V0 into square root of C by L into sine of 1 by root LC into T. What is 1 by root LC students? Here 1 by root LC equal to omega naught. That point to remember. This is if initial voltage. What is the peak voltage across the capacitor? the peak voltage across the capacitor is 2 Vs plus V0. If it is negative is given, you take the positive Vs. Easy to remember. No need to by heart. This is the peak voltage across the capacitor. Peak voltage across the capacitor, students. Very important. Please concentrate. Then what the peak current? The peak current equal to Vs plus V0 into square root of C by L. Yes. The one more case I am giving, students. IL of 0 equal to the initial current in the inductor is 0. Then initial voltage across the capacitor is plus V0. That is the positive voltage. It is the plus V0. That is the positive voltage, students. Positive voltage. Then what is the current? The I equal to Vs into, that is Vs minus V0 you take. Here plus V0 is given, you take minus V0. I am not giving total derivation, students. Not required. C by L into sine of 1 by root LC into T. Easy to remember. Then what is the peak voltage across the capacitor? The peak voltage across the capacitor is, it is 2 Vs minus V0 you take, students. 2 Vs minus V0. What is the peak current? The peak current equal to Vs minus V0 into square root of C by L. In this case also, the thyristor conduction time. What is the thyristor conduction time, students? The thyristor conduction time is pi root LC. It is also pi root LC. Even previous case also, the thyristor conduction time is pi root LC, students. What is the thyristor conduction time? In this case also, thyristor conduction time pi root LC. Thyristor conduction time is pi root LC. Yeah, these points you remember with respect to concept of LC circuit. It's no Chetan. This mainly I am giving only devices. With respect to devices point of view only that I am giving. Total will not complete because it's a 2-hour session. Thyristor conduction time equal to pi root LC, students. It's with respect to devices. I already taken the marathon sessions with respect to rectifier, choppers, inverters, AC voltage control, cycloconverters, all the problems, questions I solved already in the same YouTube channel, students. Please go through that one. That's why mainly I am giving because I solved less number of questions on the devices. That's why I am giving the important points with respect to devices. I am giving the important points with respect to devices, students. This is called tank circuit. Without any supply, yes, friends. If it is given the tank circuit, I already solved the questions, remaining topics. Please go through that session, students. This is V0, this is C. Then what is I equal to? I equal to V0 into square root of C by L into sine of 1 by root LC into T. Okay, this point also you remember. With respect to tank circuit. Okay, this is the tank circuit, students. Okay, this is the tank circuit. Yes, friends, these are the, with respect to devices, whatever the points it is important that I given, please go through these points, students. Okay, this is about today's session. Once again, I am repeating, students, whatever the important points with respect to AC voltage controller, cycloconverters, rectifiers, choppers and inverters. I solved already questions. Please go through that questions. You can get all the formulas from that questions. Yes, I already solved, students. Please go through that one. Yes, friends, for time being, yes, I am not solving all these. Here there is one announcement, students. This is BYJU'S exam preparation. Yes, flat 25% off on online classroom program, students. Plus 25% off on online classroom program. Yes, friends, use the code of extra 25. Then get the flat 25% for GATE, ESC and PSUs. Who are the aspirants for GATE, ESC and PSUs? Please utilize this opportunity, students. This is the September special sale, flat 25% off, students. Yes, students, this is Electrical by Surendra Babu. Who are not joined still now, you please join this Telegram channel for more updates about my lectures. And if you have any doubts, clarification, you please share your doubts in the channel, students. You please share your doubts in the channel. Yes, students, this is our BYJU'S exam preparation, the most comprehensive preparation app for all the exams. Get this BYJU'S exam preparation app, get in Google Play, students. Yes, students, I given all the devices concept, students. Please, because for time being I am not completing the total power electronics concepts, but I already taken the sessions. Most very important model of questions. You please solve that questions only. That is enough for your BARC preparation. That is enough for your BARC preparation, students. Yes, students, thank you very much. I am ending the session. Thank you very much, students.